All right, the last bit of information that I have to share with you is parallel circuits. Parallel circuits. Parallel circuits is in blue for no apparent reason. All right, so we have some requirements for a parallel circuit. Just like we had with the series. And there are 4 of them. 1, 2, 3, 4. And those would be 1.
Power supply.
Power supply. What is our power supply for most? Battery or a plug-in source of some sort, or a generator or an alternator, something like that. So power source. What else? Conductor. And a load. Well, gotta be loads in this case. Couldn't have a parallel circuit with one load. And multiple paths. Multiple paths for currents. All right, so if we look at a parallel circuit, if we only have one load, what kind of circuit is that?
Series.
Because there's only one. If I do this, now we have multiple paths and parallel. We'll do 3. All right, Ohm's law. Heard of the guy? All right, sometimes I have the joke, well, it's Ohm's law, not Ohm's suggestion, because you guys will do something and be like, well, that's what it is, though. Like, it can't be. It's not Ohm's suggestion. So Ohm's law, where E equals I times R. So everything stays the same as far as that goes. Ohm stays the same. So Ohm's law is the same as for series. But Kirchhoff is different. Kirchhoff's is different, but different in a mostly easy way. So, all right, Kirchhoff's laws. Well, Kirchhoff says the current is different through each load. The current is different through each load. Which is to say I total is equal to I of 1 plus I of 2 plus I of 3. What does that sound like in series?
Sounds like voltage.
Voltage. Voltage in series, we added up the voltage drops of all of the resistors, and the current was the same. Well, now we're saying the current has to be added up through each one, and that should make perfect sense, because if we have this drawing right here and we have current, we'll do it this way, conventional theory, leaving, and the electrons are flowing this way. When they get to this point, some are going to go that way and some are going to go that way, and then it's going to come this way, and some are going to go that way, and some are going to go that way. And so we have to add up the current flow between 1, 2, and 3. And if we add up the current that went through 1, 2, and 3, we would get the total current. It just splits up, because electrons can't flow through all of them at the same time. So it does that. It runs through here, the electron's going to go that way, and then it's going to return. It's going to run through this way, come down, and return. And run through this way, come down, and return. All right, so current, the different through each load. 2, the voltage is the same through each branch. which is to say the voltage total is equal to the voltage of 1, which is also equal to the voltage of 2, which is equal to the voltage of 3, and so on. That sounds like what in series? So we're just taking the current and voltage and swapping the rules. And the reason why that is, clean this up a little bit. If we think about taking a voltmeter and putting a voltmeter across here, if I put a voltmeter, and we'll say this is 12 volts, and I put a voltmeter, I'm just going to use one color, and I put it right there, what is my voltmeter going to read? 12, so that's going to read 12 volts. Well, if I put it right here and right here, it'd be the same because I really didn't move it very far. I just went from right here and just went there. So it's the same wire, right? And so then if I take it and I put it over here, that's still the same wire. So it's going to read 12, and this is also going to read 12. Well, if I put it right here across that resistor, what's it going to read? It's read 12 because it's the exact same wire I was on just a second ago. Same thing if I put it here. It's going to read 12. So the voltage drop across every resistor or load, assuming there's only one load in the series branch, is going to equal the full drop of whatever the battery is. And this is the way aircraft, homes, cars, pretty much everything is wired in series. And the reason why is a couple reasons. One, if one component goes out, it doesn't affect the others as far as the voltage and the current goes, sort of. Two, supplies the entire amount of voltage to the component. Imagine if you had a whole bunch of lights in series. First of all, if you try to turn them on, they'd all turn on at once. You couldn't individually turn them on and off. But every time one burned out, then they'd all burn out, like Christmas lights on a tree, your Christmas tree. Or, that's something else in mind, but it doesn't matter. All right, then we have resistance. And resistance is a little goofy. So R total is the inverse of R1 plus the inverse of R2 plus the inverse of R3, on and on and on, and it's actually the inverse of all of that. And I will explain that in a second. There are a couple of rules with resistance that will help you. So rules, let me see. When resistors are connected in parallel, the total resistance of the circuit decreases. Also, the total resistance, which is R total, is always less than the smallest resistor. When it comes to resistors in a parallel circuit, there are other formulas. I only memorize this formula. I only use this formula because this formula works for all occasions. There's some other ones that are like, well, if you have multiple resistors of the exact same value, then you can do it this way. There's another formula for how do you figure out the resistance if you have multiple resistors and one is missing, but you have the total? What is the formula for that? I do not teach that. You're welcome to learn it. And the reason why I don't is because I want you to be, the KISS thing, keep it simple and succeed, or keep it simple, stupid. This formula will work for absolutely everything. There is one question or two on the FAA exam where they give you, like the example I just gave you, they'll give you the total resistance. They'll say, like, there are 3 resistors in parallel. The total resistance is this. Resistors 1 and 2 is this. What is the third? You have 3 choices. All you have to do is try each one of the A, B, and C. Doing this method, and you'll get the total. So, all right. So let's try just that for right now. So let's say we had 3 resistors in parallel, and I'll just make up some numbers. We have a 10 ohm, a 20 ohm, and a 30 ohm. What is the total resistance? Our total equals what? Now, the way you're going to do this on your calculator is very simple. Let's go up to here. And we are going to use this x minus 1 key. X minus 1. On some calculators, that is the same as the 1 over x. Sometimes I'll say 1 over x accidentally. I mean the x minus 1. So to do that, we would do 10 x minus 1 plus 20 x minus 1 plus 30 x minus 1. And then hit equals. And just hold right there. I'll catch up with you. So we got 10 x minus 1 plus 20 x minus 1 plus 30 x minus 1 equals. And you should have an answer right there going 0.183, repeating. Everybody have it so far? Okay, that's the bottom half of the equation. Remember, the equation is 1 over R1 plus 1 over R2 plus 1 over R3. So we have to take care, we've done the bottom. Now we have this answer, 1.83. We have to remember that it's actually 1 over. So to do that, hit the x minus 1 key one more time. And then equals. And you should get 5.45, and that is in ohms. Did everybody get that? Yes? No? Did anybody not get that? You did not get that? No. Okay, try it one more time with this one, and we'll move forward. So clear it out. 10 x minus 1 plus 20 x minus 1 plus 30 x minus 1 equals, now hit x minus 1 and then equals. Got it? That's how you do it. And we got 5.45. Now, before I move on from that, what were my 2 rules? Well, actually, the second rule is the one that's going to apply. The total resistance is what? O is less than the smallest resistor. So, there we go. Is 5.45 less than 10?
Yes.
Yes. Now, why is this? And I thought about, well, how can I explain why this is? And when I was in the Navy, I lived on Treasure Island, and my ship was often inside, there was a shipyard right down inside where I think where the ballpark is now. So I went to San Francisco an awful lot, so I spent an awful lot of time going through the Bay Bridge and paying tolls. You guys been through the Bay Bridge and pay tolls?
Sucks.
All right. What's that?
Sucks.
It sucks. Okay. Imagine, if you will, a toll booth. That many toll booths. How many toll booths are there? 5. We'll say there's 20. And instead of having 20 all lined up like that, we took 20 of them and we lined them up one after the other. So when you left here, you'd go 10 miles and you hit a toll booth. And you hit another 10 miles and you hit a toll booth. Another 10 miles, you hit a toll booth. That sucks worse, right? That's toll booths in series. So every time you go through a toll booth, it takes you 5 minutes. So you have 20 of them, you figure it out. That's how long, 20 minutes, whatever it is. 2 hours, something like that. So 5 times 2. So anyway, take you a long time. So that's toll booths in series. But we take those same toll booths and we put them like they are now. There's multiple paths. We call that parallel. Okay, so you have one toll booth open and you have a line of cars going way back. It takes well, back in the old days, you actually had to stop and give them money, but now you just kind of drive through. So every time you'd stop, it would take 15 seconds per car. So it takes 15 seconds per car. You only have one toll booth open. A toll booth is a restriction, right? Okay. So a toll booth is a restriction. If I open up a second one, it still takes 15 seconds, but the total time that all these cars have to wait was just cut in half. They've got 100 cars they got to get through. Now it's cut in half. Open up another toll booth, which is also a restriction of 15 seconds per car, but now you've got 3 lanes and your time is cut in thirds. So it's the same way with kind of resistors, if you want to think about it that way. Every time you open up another branch, it's another way for the little electron cars to go, and so they can get through faster. So the total resistance actually goes down. So if I had a branch, a circuit like this, and I took out this end resistor, would the total resistance go up or down? Be more resistance. And if I add another resistor over here, the total resistance goes down. Okay. Well, that's all there is to it. Not much. You got that, you got it. What I was saying, though, earlier is something like there is a formula that said, well, there's a 3 resistor circuit and the total resistance is 5.45. There's resistor 1 has a 10 ohm, resistor 2 is a 20 ohm. What is the last resistor? What is the ohmage of that? And of course, your test would have A, B, and C. And it would say, 30, 40, or 50 ohms. And so how would you solve for that? First, I would plug in the 30, and I would do the whole thing and see what it came up with. And then try 40, then try 50. Just do 10, 1 over x, 20, 30, 1 over x. Figure it out. Right there, you'd be done. I actually think it's easier than that. It's something more like, I don't know, you can actually eliminate them really easy because it's almost like one of them is 30, one of them is like 4, and another one is like 3, and you can just look at it and go, well, wait a minute. The total resistance is less than the smallest resistor. This one is bigger and that one's bigger, so you can eliminate 2. I think that's how the test actually works. It's just so easy. But anyway, just plug them in is the point. So let's do some examples. I can find some. Here we are. All right, so it looked like this. So we have E, I, R, and P totals of 1. These will be of 2. And our givens here will be, let's see, 12 volts. And we'll do 6 ohms here and 4 ohms there. You want to just go for it? You want me to work it with you? All right. All right, ready? What's the first thing you did? What's that? Voltage. You went voltage. 12 volts. 12 volts. Because voltage stays the same. Now what? Ohm's law for what? Current. Okay. We can use Ohm's law. E equals I times R. And again, you can maybe did it in a different way. That's fine. So we want to solve for I right here, which is 12 divided by 6, which is 2 amps. And over here, 3 amps. Carried over here, so we can solve for I, which would be 5 amps. And then we can do R equals E, 12 divided by 5. Or we can do 6 1 over X plus 4 1 over X equals 1 over X. So what did you end up with? 2.4 ohms. Does that check out? Is that smaller than the smallest resistor? Yes, it is. So it checks out. And then solve for pi, which is I times E, 12 times 5. 60 watts. 24 watts. And what, 36 watts? 36 watts. 36 plus 24 checks out at 60. So we're good there. Easy? All right. Let's see if we can take it up a notch. Got some notes. Here we go. This one. Maybe if I could just go like this, save some time. SeaWorld. This, of course, will be total. This will be 1, 2, 3. Okay, we'll go again with 12 volts. I will give you, let me see, 3 ohms, 6 ohms, and 12 ohms. You got it? All right, how'd you do it? Total, okay, what's total resistance? 1.7 ohms, what I heard. Okay. Now what?
12 volts all across.
12 volts across. Then Ohm's law, where E equals I times R. So I is 12 divided by 12, which is 1 amp. 12 divided by 6. 12 divided by 3. 1 plus 2, well, we can do this. 12 divided by 1.7, I'd rather not. 4, 5, 6, 7. 7 amps. Check it out. 12 divided by 7 is 1.714. So that checked out. Going E divided by I is that. And so everything checks out. Looks good, yeah? Yes.
Wrote the 7 ones that are right, or?
No, get the hell out. I don't ever want to see that. No, I don't care.
So 02 is not okay?
02?
I got 7 points. Well, I can say it wrong,
All right. Boy, so much for save time, see world. 3, 1 over x plus 6, 1 over x plus 12, 1 over x equals, 1 over x equals. The actual answer is 1.714285714. So you could put 1.714, you could put 1.71 or 1.7. All those answers are correct. Do what you like. So there's no rounding there. Only thing you couldn't put is 1.7142. That would be wrong. Why is that wrong? Because the 8 makes that a 3. So 2 would have been wrong. All right, let me see if I can make a difficult one here. You guys are too freaking smart. I don't think I can make it very difficult. Let me see. No, it's just hard. Once you know how to do it, it's like, really? That's easy. This one's probably easier than the last one. Done already?
Yeah.
Everybody's got it? What'd you do first?
Added up the amps.
Add up the amps. How many amps do we have?
6 amps.
6 amps. Now what?
Solve for volts.
Solve for volts. You mean voltage total?
Yes.
Okay. Voltage total, which is
12.
EIR. So you want to know E. It's I times R. 12 volts. Then what'd you do? The obvious choice. Fill this out. And then solve for R, where E divided by I is R. So what do we end up with?
24 ohms.
24 ohms. 4 ohms. And 4.8. And then we will see that 2 is smaller than the smallest one. So it all checks out. All right, one last one. Let's see here. Oops. Okay. Did I stump you on this one? I see somebody's still working. Everybody done? Okay, what'd you do first? Voltage. What's voltage? 3.5, 3.5, 3.5. What'd you do next?
Resistance, total resistance.
What's that?
Total resistance.
Total resistance is what?
3.96.
3.96 ohms. Okay. Then what?
All of the rest of the I's, 3.5 divided by whatever the resistance is.
5. Which is what?
5 or
It's 5.
oh,
Three-
sorry. Actually, yeah, that's what I guess.
What'd you guys get for this one? 0.7 amps. Okay, 0.7 amps. Well, I can't do anything there. How about this one? 43 milliamps. Okay. Well, now what?
Solve for I in line 3.
Solve for I. How are we going to solve for I?
Subtract those two from the total.
Subtract those two from the total. So I might want this one in milliamps. 0.00. Oops. 0.007. 07. If it's 0.7 amps, it's 0.007. So what do we end up with?
0.14 amp.
0.14 amps. Everybody agree? All right, 'cause I don't have the answers in front of me. Then we just solve for this one, which is
25.
how much?
25.
25 ohms, and we could double check. This one is less than that one, so that kind of checks out.
8.7 amps is.
Would that be 700 milliamps?
Oops, sorry, yeah. I went the wrong damn way.
Yeah.
1, 2, 3, 700 milliamps. My bad. Oops. All right, that's about, without making it really difficult, that's about as difficult as it can be. After this just comes, the components become difficult. Instead of having just a load, then you start adding motors to it. Like you have a, quarter horsepower motor that's 80% efficient. So you have to figure out the math on that one, but it's all the same stuff. So
You just do 80% of a quarter horsepower, and then that's your. Oh.
not 80% of, it's 80% efficiency all the other way around. So if you had a 1 horse, we'll do that in the next class, but if you have a 1 horsepower motor, that's 746 watts. If it's 80, and that's the output, if it's 80% efficient, then that means that it takes more than that to get the output. So you have 120 input. But we'll do that next class. Not this class, but Aero 300, AMT 300. But we'll get to that when we get to that. It'll be real easy when we get there. Just explain how to do it, and there we go. So, all right, any questions? All right, I did make parallel practice problems if you want them. If you don't want them, doesn't hurt my feelings. We will have a quiz on this tomorrow. Want to hand them out?